All right, so online close. For this one, they're asking us, or they're telling us, an online clothing retailer keeps track of its customers' purchases. For those customers who signed up for the company's credit card, the company also has information on the customer's age and income. A random sample of 500 of these customers shows the following scatter plot. And it's the total yearly purchases by age. So this is the age, right? So they're just plotting the age of the customer and then their total purchases. Now this is a very dense scatter plot. So do I draw the line this way? Do I draw the line this way? Do I draw the line this way? It's kind of hard to tell, isn't it? Well, what do you notice? Well, it says that the correlation coefficient of this thing is 0.037. That is almost an anti-correlation, right? In other words, this thing is just a big cluster of data. There isn't a pattern, so it'll be hard to make predictions on this, okay? So then the summary of the data is that the mean for the age is 29.67 years. That has a standard deviation, when you look at the distribution of the age, of 8.51 years. The total purchases, the mean is 572. The standard deviation is 253. So if you wanted to know about what the maximum was, you'd take that standard deviation, multiply it by 3, and add it to the 572. Right? So it'd be about $1,200, $1,300 is the max. The minimum purchase is 0. So we'd have to think about that. It may not be distributed normally, or it may be skewed, because if I multiply, this is about 750. If I subtract 750 from 572, I end up with a negative number. So I would just assume that data is skewed. And that's okay. So anyways, let's focus on the question though. What is the linear regression for predicting the total on this thing? Okay. Now, which one was this? 43? 45, yeah. I know I've asked that about 5 times. So we just basically do the same thing that we did on the last problem. Okay. So we're gonna start to find the, let me get in here and make sure I have enough room. So for A, to find the equation, the first thing I need to do is find the slope. So remember, what we're trying to get is y hat is equal to b naught plus b sub 1 times x, right? And that's kind of like y equals mx plus b, but it's different, right? So remember that B1 is going to be RS, total sales, the dependent variable, right? All over the standard deviation of the age. And we call that the independent variable. In stats, they use a different terminology. They say that one depends on the other. What's the term they use? I forget now. Doesn't matter. So when I plug that in, yeah. They're trying to say one doesn't have an impact on the other, but you're kind of suggesting it. Okay. So then my all the information is given to me. The R value, they tell us, is 0.037. The standard deviation for the total sales was 253.62. All over the standard deviation of the age, which was 8.51. If you crank through the math, that gives you, I think, 1.1027. Okay. Then we got to come back to this equation and we say y hat is equal to b naught plus, but now we know what the slope is, 1.1027 times x. And we plug in the numbers. We know that based on the summary, the mean is this and the mean is this. So I'm going to plug this in for x. So this is my x value, and this should be like my y value, or what we would say y hat. And this is an approximation. This is the technique that we use to approximate what the y-intercept would be, because that's what we're solving for. So I'm going to say 572.52 is equal to b naught plus 1.1027 times 29.67. Oops. And I'm not going to bore you guys with the algebra, but if you crank through that and solve for b naught algebraically, you'll get 539.803. So then my final equation will be that the total sales, the predicted total sales, is equal to 539.803. And you could leave it like that. That's how the textbook has it. Plus 1.103. They did round this. That's funny. This is, anyways. Times the age. So that is, this is the answer. In other words, the total purchases is equal to all this stuff times the age of the customer. But it has a really weak correlation. So this is the line of best fit, but because it has such a weak correlation, in other words, if I plug in somebody's age, it's going to crank through the math and give me a spot somewhere here, and wherever that is. And then I have this line. So if I were to graph this line, it goes kind of like this. It's going to cross the y-intercept at about 530 and have a very slow thing. Well, I could have a point up here. I could have a point up here. And that correlation coefficient, the R value of 0.03, lets me know that the predictive value is not so helpful. But I still have a range. I could still approximate a range of where that spending will be, okay? So it's not helpful, but it's more helpful than nothing, okay? Does that make sense? All right, so now let's move on to part B. Part B says, do the assumptions and conditions of the regression appear to be met? Now remember, that is, what are those conditions that we talk about? Well, I would say yes. Same as the last problem. The total and the age are quantitative. So that's good. This next one I would almost kind of disagree with the authors, but I see what they're trying to get you guys to focus on. It is straight enough. Because it's a cluster, it doesn't seem to curve. All right? So what they should say is it's not a curve. But you could draw a line through that data, and the data appears to be straight enough. It's a very thick line, but it's straight enough. Because the data is so dense and it's so broad, it doesn't seem like there are single outliers. It seems like the whole thing has outliers. It doesn't seem to spread, though. It seems to be consistent based on age. So if we read this data, if we read this scatter plot from left to right, if that line goes through here, I mean, there's just a lot of data and it's a huge spread. Now, that's based on the scale. Where we run into a problem is remember this line represents y hat, and if I got something way over here, it's a tremendous underestimate, and if I've got something here, it's a tremendous overestimate. So when it comes to estimating, it isn't the most helpful, but it is. You can run find a regression line, and it is kind of useful. You could at least come up with a range. So anyways, now part C wants to know what is the predicted average for somebody that's 18 years old and for somebody that's 50 years old. So that one is simple. That's just plug and chug. So let me give myself enough room. So there's two things. I'm going to say the total predicted value. I'm going to do the 18-year-old first. 803 plus the 1.1. I'm just going to plug in 18 years right here. Now when I do that, I get $559.66. And now if I do the same thing for a 50-year-old, same equation, except I'm going to plug in 50 for x. That is going to be 594.95. So what does that tell me? Well, first of all, it's a weak correlation, so I'm going to think to myself, the average for the 18-year-olds will be about 559. But it could be as high as 700, and it could be as low as 0, or 200. You got to look at the graph. All right, if I look at the graph, 18 would be about right here, and as you could see it, that's about where the average would be. The middle would be 559, but it could be as low as 0 and could be as high as 1,000. For a 50-year-old, because they have a few less bills and maybe more income, they probably spend more. Okay. So now Part D wants to know what is the percent of the variability of the total yearly purchases is accounted for by this model. Well, now that one we just need R squared. That's all we need to do. So to find R squared, that is equal to R squared, which is equal to 0.037 squared, which is 0.0014, or about 0.14%. So we got, whoops. That is a horrible percentage sign. Okay. And then lastly, for part E, let's see what part E says. Do you think the regression might be useful? Might be a useful one for the company? Yes or no? What do you guys think? Yeah, so I would say probably no, because it's too broad. Not really. Observed values are too far. I should probably put the word some. Observed values are too far away from the predicted values. Now, what am I really saying? That it has a high residual, right? Remember, the residual is the observed value minus the predicted value. And also, that's also how you find R and R squared. And it's the sum of least squares and some other stuff, okay? Any questions on this stuff? Does this make sense to you guys? Okay, good.